with the pleasure and honor to be here to share with you guys our recent research results. So as the title of my talk suggested, so today I'm going to mainly focusing on the AC-OPF power flow problem by deep learning. So I will cover some practices, tricks here and there, and also share that on the theoretical foundation of this topic. So here is here's the outline of my talk today. I will start with a brief introduction of AC-OPF problem in case that some of you are not very familiar with the task. And pretty much we are going to focus on 3 different works that we have done on this very important research effort. The first one is the unsupervised learning framework using the Lagrange duality. So in this work, essentially what we do is that we come up with a complementary Lagrange function, incorporate the constraint violation into the loss, and we're using this Lagrange function directly as the training loss to try to predict the OPF solution. So that is the first work. Second one, we switch from unsupervised learning to the semi-supervised learning. The semi-supervised learning means that we have some ground truth labels for the decision variables, and we're going to use those ground truth labels data trying to augment the data set to provide some pseudo measurements. And in this work, the most important thing or the contribution that we have here is we have a physics-informed gradient or Jacobian estimation. So by doing this, we can really accelerate the training process for the deep neural networks. So these 2 works are pretty much focused on the general AC-OPF. In general, this is a hard problem, highly nonlinear, and non-convex. So some of you may have heard this fancy word, non-convex, which means that there can be many local minimum solutions. It's really hard to get a global solution. So the last one, so this is focusing on the convexified OPF. So we convexified the nonlinear, non-convex AC power flow equations. We are going to focus on that type of problem. And we have this constraint screening. Here, the constraint screening means that we are going to proactively identify which constraints are active or inactive. We are going to delete those or remove those non-bounding constraints because they are redundant. So in this case, we can reduce the size of the constraints. This can really accelerate the solving time, even with the conventional solver. So for this last work, we have a very good idea with this mixture of experts. So basically, we have different neural networks in the same framework, and then we're trying to leverage the advantage of each of the neural network in order to improve the classification performance of this last one. Towards the end, this is the summary. I will give you takeaway points and some discussions of the future works. So I don't know how fast we can go. There's still some time left towards the end. I can also quickly go through some other efforts that we worked on for the load forecasting, for the power system event detection. So the very first one is the big picture of the AC-OPF power flow problem. So it's essentially the task is try to determine what is the best operating point in the steady state for our power system. In the meantime, we need to respect lots of constraints, try to make sure that the power generation and network constraints, they are going to be satisfied. So this is the big picture of the task about AC-OPF. So the goal actually is quite clear. We want to minimize a certain operational cost. For example, for power system, the typical cost is the total generation cost. Of course, you can also consider about the cost of active power line losses. These are the 2 main popular objective functions. While in the meantime, while we're minimizing this operational cost, we want to ensure that the power generation and diffusion, they are going to be satisfied within the physical limits. For example, we need to satisfy voltage magnitude within certain lower and upper limits, phase angle limits, flow limits, so on and so forth. Actually, there are quite many variants built on this AC-OPF problem. Right? For example, you can consider about multi-period formulation. Right? You're not only going to decide what is the optimal operating point for the next hour, you want to decide for the next 24 hours or even longer. So this is about multi-period AC-OPF. There's also N-K continuous analysis, which means that we want to make sure that the system is robust enough in case that some of the power lines or maybe some of the power generators fail, right? Then we still be able to operate the system normally. So this is the N-K security constraint OPF. So you can also try to solve this AC-OPF in a decentralized fashion, right? There are many distributed algorithms. For example, this ADMM, probably is one of the most popular one. We can also consider about some consensus algorithms, some Lagrange relaxation techniques, trying to solve this large-scale problem in a decentralized fashion. So finally, if you consider these days we want to get high penetration renewables into the grid, right? We want to make our future power system more sustainable, greener, right? So we want to incorporate the renewable energy from solar, from wind to support total demand. So whenever you have these renewable energy sources, there is an inherent uncertainty with this supply. Right? We don't know how much energy we are going to capture from the sun, from the wind next day. So you have to deal with this inherent uncertainty or fluctuation when it comes to the day-ahead scheduling. So people already came up with very good tools. Usually it's coming from the stochastic and robust optimization framework. We either have a stochastic optimization problem. We can consider about average cost, expectation. You have the chance constraint. Right? You want to satisfy the flow limits with high probability. You have the conditional value at risk, CVAR. Right? This is the very popular tool in the financial area, so on and so forth. You can even postulate some uncertain data sets. You don't know where exactly the wind or solar power are going to generate. So you can have affine or polyhedron, or maybe ellipsoid uncertainty sets. So this is about robust optimization. And finally, there's something in between. It's called distributional robust. So this is something between the stochastic and robust. Because usually robust, you're trying to solve a minimax problem, right? It can be quite conservative in terms of decision variance, right? So if you want to trade off the conservativeness about and randomness in between the stochastic and the robust, there's a distribution robust. Right? Over there, typically you need to consider certain metric like KO divergence or maybe the Watson distance. So this is kind of state-of-art efforts or formulation about AC-OPF. But however, actually, even without those many different variants, even the very basic single period formulation turns out that this AC-OPF problem is a highly nonlinear, non-convex problem, which means that it's really hard to find a global solution in an efficient way. And our efforts right now, until now, we're going to focus on this very basic single period formulation. And hopefully in the future, after we have a success with this single formulation, we're going to extend it to the multi-period or even some other variants. So who solved this problem, AC-OPF? So it turns out that many market participants, they have to solve this problem every day or even every few minutes. Energy traders, right? So they need to solve this AC-OPF problem in order to predict the electricity prices for their market bidding. Large utility companies, for example, PG&E, right? They have their own assets, the generators. They need to solve this AC-OPF problem to come up with efficient hourly scheduling. And on top of them, there's an independent system operator or regional transmission operators. Of course, they get the bids from both supply and demand side. They also need to solve this AC-OPF problem either in the day-ahead fashion or maybe in the real-time markets. Right? So the outcome of this procedure, usually called market clearing, they need to figure out what is the most efficient scheduling for the generator, and also they also need to find out what is the location market prices. Right? This is like a byproduct. Okay, so as we can see that this AC-OPF program is really sitting in the core position of the power system operation. Right? So from both academia and industry, many people, many groups, researchers have put lots of efforts over the last few decades trying to improve the methodology solution for this AC-OPF. The ARPA-E, back in 2015, they hosted this competition. It's called Grid Automation Competition. So this competition actually lasted for almost a decade, from 2015 to 2024, about 9 years. So it is the longest ARPA-E project in its history. Essentially, this competition consists of 3 different challenges, or you can say 3 different stages. the first challenge to C1 pretty much focused on a large-scale security constraint AC-OPF. Okay, so they had $3.4 million in prices if you can come up with a good solution for this large-scale security constraint AC-OPF. And then the two remaining challenges, C2 and C3, they just build on C1 and add unit commitment and multiplier dynamic markets and topology optimization into C1. And so this is like OPF is really the building block. And then if you want to schedule the generator, which generator turn on, turn off at which time, then you have this unit commitment. Right? You want to decide which generator, which unit you want to commit into the system. And finally, it's about markets. Okay, so this is really important problem. And also, if you consider about high penetration renewables, this simply enabling two-way power flows. Right? Conventionally, traditionally, the electricity is always flowing from generators, goes to transmission, diffusion, and reach to our end users on one direction. But nowadays, you think about rooftop PV panels, right? Almost all the houses, especially here in California, there's a mandate in that after 2020, January, almost all the new houses, they must install the PV panels, right? Then you can generate electricity from all the residential houses, all the buildings, and you can even feed back these redundant renewables from solar back to the grid. Now we have two-way power flows. So if you want to schedule these renewables, as I mentioned before, right, there's uncertainty, and you want to solve this AC-OPF problem more frequently. Right? You want to get solution faster, in a more reliable way. There's quite growing need trying to find the fast and frequent OPF solutions. Now, if you look at the history of the algorithm of the methodology for the AC-OPF, so the very first rigorous mathematical formulation was established around 1967. After that, as I said, many people have put their efforts trying to improve the solution technology here for the AC-OPF. The early era is between 1960s to 1980s. At that time, we only have the tools from linear programming or quadratic programming. They're relatively easy to deal with, but clearly, right, because they are not able to handle the nonlinearity in general. So after certain years, people probably pretty much forget about LP or QP for a general AC-OPF. For the special cases, maybe we can still call the LP or QP solvers to deal with it. For example, like DC-OPF, and usually it ends with a linear program. But for the more general nonlinear AC-OPF, those LP, QP, they are not good enough. Then move on, when we get into 1990s, there are lots of nonlinear programming tools or algorithms for modeling the nonlinearity constraints more accurately. And the two famous one is the sequential quadratic programming. Basically, you just approximate original function using a quadratic function, and you sequentially successfully solve the problem. The other one is the workhorse these days for many of the commercial solvers, is so-called internal point method, IPM. Right? Actually, it turns out that there are also lots of different variants of the internal point method people have developed in order to tailor it into the spectral structure of the AC-OPF. So generally speaking, they can handle large scale, even for some non-convex problem. But for the non-convex problem, usually we cannot guarantee global optimality. At best, probably you can claim about local solution, or maybe sometimes you even end up with a saddle point, which is typically not that interesting in terms of the operation cost. And for the internal point method, they are not really very scalable for large networks. So the next stage, right, we're going to get more and more advanced technologies in 2000 to 2010. For example, we have this augmented Lagrange, which we are going to talk about today. There's a trust region method, all this kind of different algorithms trying to improve the convergence of the iteration. And around 2010 or 2012, so people have developed this conic relaxation from the second order cone programming, from SDP relaxation, and for example, by Javad Lavai and Stephen Lowe, they are the probably very first group people establish some sufficient conditions saying that under this condition, for example, topology of the power system is a tree network, right? We're talking about diffusion system. There's no cycle. If the load satisfies certain conditions, then this relaxation is exact, meaning that after you solve this convex relaxed problem, you get solution. That solution is going to be the global solution, even for the original non-convex problem, which is a good news, right? But however, for a more general setup, if those conditions are not satisfied, then you cannot guarantee the tightness. If you go with the stochastic OPF, with large networks, you have the binary variables, for example, from unit commitment. Then you could consider bandless decomposition. You can consider this progress hedging. This is the popular decomposition techniques. Now, finally, we reach to the current time, starting from 2020, actually probably a little bit earlier, 2017, 2018, because these days is AI for science, AI for this, AI for that, it's AI for everything, right? You can imagine that, of course, power people, they want to really utilize the state-of-the-art tools from AI, from deep learning, trying to improve the power system operation, right? So in this category, the deep learning using the convolutional neural network, using the recurrent neural network, using the graph neural network, and many other architecture, people have already trying to see that, okay, how the performance of these deep learning deep neural networks for the AC-OPF, or maybe for some other power system operations. And even very recently, I guess just a few weeks ago, I checked some literature. I found that people already trying to see how about large language models, those foundation models, can we use them for our system? Okay, this is definitely an emerging topic you want to look at. Okay, so this is like a brief history, overview of the AC-OPF program. So if you have some junior graduate student here, if you are still looking for some interesting research topic you want to work on, I have to say AC-OPF is definitely one of them you should pay attention to. So let's get into the very first talk. The very first topic, the unsupervised learning via the Lagrange duality. So essentially, we build up from the literature, right? We are inspired and motivated from the lots of very interesting results from literature. So we already mentioned about nonlinear programming. So usually they are heavy computational burden, right? Because conventional solvers really takes longer time to get the global solution or even local solution. They are not that suitable for the real-time applications. For the SDP, semi-definite programming, or even the DC-OPF formulation, right? So it turns out that, generally speaking, their solution may not be even AC feasible, right? You solve the easy problem, but solution is not really even feasible to the original problem. Okay, it's not that useful. So this DC-OPF solution is not feasible to the AC case. I think recently was pointed out by my colleague Carrie Baker a few years back. And then if we talk about the deep learning, we can basically classify them into two categories. One is the supervised learning, the other one is the unsupervised learning. Right? For the supervised deep neural networks, there are many works here. Right? So essentially, we have the ground truth label. We know what is ground truth values for the decision variables. We use them as the supervisor, as the target, as the guidance, trying to train our neural network in order to accurately predict the OPF solution with some unseen low demand inputs. However, many of these works, there are some kind of inherent limitations. For example, some of the papers, they just simply ignore some key constraints. They simply ignore or relax the difficult constraints. This will result in large degree of constraint violation, or maybe we have a load mismatch. So here, load mismatch means that for the AC power node, for the AC power flow equations, it cannot be satisfied perfectly, right? We have the mismatch between the load and the generation. And more importantly, for the supervised learning, of course, we need those supervised, we need those ground truth labels, right? So how can we come up with those ground truth labels? These are all generated by the conventional solvers. Even you have the history data, we know that we are running OPF every day or every few minutes. You can have a history data from certain area over the past few years, but all those history data, essentially, we obtain them by using the conventional solvers, right? So again, conventional solvers takes time to get those true labels. And also, even for the conventional solvers, we cannot guarantee that the ground truth labels, they are really the global solution. Now, for the very first work, we are focusing on the unsupervised learning framework. Unsupervised means that we don't even know the ground truth labels. We only have input of program, which is the active and reactive power demands. We want to predict what is the minimizer of the decision variables. Okay, so we have two key references we rely on. The first one is the DC3 by this paper from Zico Kota's group at CMU. So this was their early work back in 2020 or 2021. So they really came up with this very nice framework trying to do the good variable splitting, and then they have very good results. So we try to compete our proposed method with this one of the state-of-the-art, DC3. The other one is from Minhua Chen's group in Hong Kong. They call their method is the deep OPF NGT. So this NGT stands for no ground truth. No ground truth, of course. Unsupervised learning is always, you don't have the ground truth labels, right? But turns out that for their method, they have different schemes. At least based on our submission result, we found that this methodology can result in large load mismatch. Okay, build on these two existing works. So our work here, which was published in GlobalCon back in 2022. So as you can see that here, the contribution or the highlights of this work is that, again, we are sticking with the unsupervised deep learning for the OPF, while the Lagrange duality, the key feature is that we build a augmented Lagrange function which integrates the constraint violation into the training loss. Okay, that's the first thing. But actually, integrate constraint violation into training loss, we are not really the first one to consider that. It's a very natural way to incorporate the training loss, to incorporate the constraint violation into the training loss. I think the big feature is that using the Lagrange duality theory, we're going to adaptively modify or update the Lagrange multipliers, which is the dual variable. This turns out to be really good to enhance the training efficiency and convergence, as we will see in our simulation results. And finally, we can use this fast decoupled power flow solvers trying to further accelerate computation. So apologize for lots of mathematical equation here, especially for the non-engineer students, but let me just spend a little bit of time to explain the details and the difficulty here. So this is a very traditional formulation of the AC-OPF program. Again, we want to minimize the total generation cost. So here the PGI is the power generation or active power output from the generator at bus I. CI is the associated generation cost. We want to minimize the total generation cost subject to a bunch of constraints, right? We have lots of constraints because we want to obey the laws of physics of our power grid. So probably the most difficult one in the feasible set in the constraints here is from 1B to 1E to 1D. So those four equations essentially is the AC power flow equation. Right? We can see that the active power P and the reactive power Q, they are really a function depending on the voltage magnitude V and depending on the voltage phase angle sigma. Right? But if you look at it carefully, on the right hand side, we can see that in the summation, each term we have this VI times Vj. This is a projected term. This is a bilinear term. And on top of that, this VI times Vj need to multiply with cosine theta and also need to multiply with sine theta. Right? So you can imagine that why this problem is highly nonlinear and non-convex. This is because of due to the laws of physics, right? This naturally will come up with this result, the AC power flow equation, the injected power, the big P and big Q, they are really not a nice function depending on the state of the system, which is the voltage phases, right? And similarly, even for the power flows, we are using the small letter P and small letter Q to denote the active power flow over the line from bus I to bus J, and here small q is the reactive power flows. So besides these four equations, the remaining constraints are relatively easy to deal with. Right? We have the flow limits constraint here, basically saying that the squared apparent power cannot be beyond a certain threshold, which is captured by this S max square, and all the other decision variables the active power generation, the voltage magnitude, or if you want, we can even add interval constraint for the phase angles. They must be within open box constraints. Okay, so this is the very generic formulation for our AC-OPF program. And with this, actually, our goal is what? We want to train a deep neural network, essentially trying to learn the underlying mapping from the input of the program to the output program. So let me go back. So what is the input of program? So the input of program is captured by all those blue variables. So the blue variables will have load demand at bus I, the active load demand. We have the reactive load demand at bus I, same, right? So if you give the program with different load demands, because we know that load demands change over time consistently, right? So if you give different load demands for this program, in principle, you need to solve the problem many times, right? Each time you get a new load demands, you need to solve it again and again in order to come up with the optimal solution, right? That is the input of program. The output of program is clear. They are all highlighted in red. They are essentially the decision variables or the optimality variables for this AC-OPF program. We have the voltage magnitude, this vector V. We have the phase angle theta. We have the active and reactive power injections or generations. And lastly, if you want, we can even consider the power flows as one of the decision variables, right? So whatever deep neural network you want to design, essentially you want to approximate this underlying mapping from the blue variables mapped into the red variables, input to the output. In this case, essentially, we are sort of solving this problem in another way, right? Not through the conventional optimizer perspective, but in this case, it's using the deep neural networks. Now, let's consider we split the output variables, which is denoted by this YO. So O stands for output. We have so many output variables. Let's first split them into 3 different groups. Okay. So we have the first group Y, which capture the power generation. We have the voltage magnitude, except for the demand bus, the load bus. While the second group, Z1, is captured all the phase angles for the voltage theta. We have the voltage magnitude at the PQ bus, which is the load bus. And all the remaining variables, this will be captured by the third variable Z2. Okay, so now you can see that we have Z1, Z2, all 3 different group variables. This consists of the entire output YO. So the motivation to do this variable splitting is that it turns out that if you do the splitting in this way precisely, then we can guarantee there's no load mismatch. We can guarantee the satisfaction of the nodal balancing equation and power flow equation. Okay, so this is a big advantage compared with many other variable splitting schemes. And with this variable splitting, finally, we can compactly formulate AC-OPF problem by 2A and 2B. Right? So essentially, all the equality constraints will be handled by the power flow solver, and probably some straightforward evaluation, as we will see in the next slides. And all the inequality constraints, what inequality constraint do we have? As I mentioned before, we have these box constraints, right? We have these flow limits. These are all the inequality constraints. This will be captured by this vector valued function H. Okay, so we can compactly say that all this constraint function H will be endwise less than or equal to 0. And let's consider about the dual variable, Lagrange multiplier mu, is associated with this constraint function. Now, this is essentially our framework trying to predict the OPF solution even without ground truth label. Right? So we get input X. Again, X is the PD, QD, is the blue variables. If you remember, we fit into our fully connected neural network. We first output the variable Y. Variable Y is the first group of variables in the YO. Right? And for the remaining Z1, Z2, they are going to be handled by a power flow solver. Right? If you give Y fit into a power flow solver, it will output Z1. And with Z1 and Y together, we figure out what is the voltage phasors at all buses. After you figure out what is the voltage phasors for all the buses, then essentially you can determine everything system, because we can simply figure out what is the Z2 variables. Okay, so this is our framework here. And we are using this augmented Lagrange function. There are some detailed mathematical derivation behind this. Let me stay at high level. So at the end, we are using this augmented Lagrange function, which is a function depending on both the primal variables. Remember the y, z1, z2. These are the output of our, essentially is our decision variables. And also we have this Lagrange multiplier vector mu, right? So if you look at carefully about this augmented Lagrange function, what we have this original objective function f, which is the total transient cost, or maybe the cost of the power, active power line losses. And this part is more like a regularizer. Right? This augmented Lagrange part is more like a regularizer, which is essentially is to capture the constraint violation. Right? So if some of the elements in the function h here becomes positive, then we need to penalize it. We don't want to be positive. We want to be all the solution to be feasible. Then element-wise, all the h here should be less than or equal to 0. Right? So this kind of penalty is captured by this augmented Lagrange. Okay, so with this is our algorithm. What we have, you get the load demand data. Right? We only have the PD and QD. We don't have the corresponding ground truth decision variable for the YO. And let's say we have n epochs, we need to train the neural network. And we get some samples from the dataset CADX. Again, these data samples, if you're talking about mini batch size, can be 32, 64, whatever mini batch size you are going to implement. Then we first compute the Y variable through the feed-forward propagation. Right? Then we can obtain the Z1 variable using a powerful solver. So the popular powerful solver is either you use the Newton-Raphson, right, which is more accurate, but probably is a little more costly. Otherwise, if you really want to with a low computational burden, we can go with the fast decoupled power flow solver. And after we figure out what is Z1 together with Y, we know everything. We can decide Z2. Just plug it into the power balance equation and the branch flow equations. Then we are done. We are done with the output of the decision variables. And finally, we need to compute the training loss, and we need to update the weights of the neural network, right? So this step is kind of standard. Go with the back propagation. We take the derivative of the loss function with respect to the weights, and you can go with the gradient descent or stochastic gradient descent, whatever the fancy optimizer you have, trying to aim for the best value for these weights for our neural network. Okay, and the new feature here in our algorithm is that different from the DC3 or some other existing works, that we are going to keep updating the dual variables. Right? So essentially, we know that we can sort of solve the original program in a primary dual fashion. Right? At one iteration, we are going to minimize the Lagrange with respect to the primary variables, and the next we are going to update the dual variable in a gradient or subgradient ascent fashion. In this way, essentially, we are solving the original problem. And here, we see that you don't even have to update this dual variable every iteration, every epoch. You can update it maybe every 5 epoch, 10 epoch, depending on this m value. Right? So this is precisely the subgradient ascent updates for our dual variables. So if you keep everything at the high level, this regularizer makes sense, right? Because this dual variables essentially is like a pricing signal to tell us that what's the cost you should pay if you violate, right? So if the violation degree is really high, then you need to pay high cost, right? So if you keep updating this pricing signal, then essentially you can get a better idea, or you can try to force constraint. Okay, so let's talk about the simulation setup. We simulated for 2 benchmark systems, IEEE 30 and IEEE 118 system. So from these 2 systems, using max power, you can get nominal values for our input, the active and reactive power demands, that we call the P tilde and the Q tilde. And how do we come up with data set? We can simply generate, for example, in this case, we generate 5,000 samples. Each of the samples is going to be withdrawn uniformly distributed in this interval, right? We have plus or minus 10% perturbation around nominal values. for both the P tilde and Q tilde. Okay. So you first extract the nominal values from that power, then you do plus or minus 10%. You have that interval, you can start doing sampling, uniform sampling, and you can get data set. And for this work, our simulation, we did it with a server with this NVIDIA RTX GPU and the training details. Okay, so for the fully connected network, actually we didn't even do fancy things. It's very basic one, just one hidden layer. That's quite really wide network. For this hidden layer, we have 50 neurons for the small scale power systems. So if you go with a relatively large one, 118, then probably you need to increase the number of neurons in that hidden layer. And actually, my student told me that for this one, if you also tried different architecture, you can even go with a deeper network, right? Not necessarily really wide. You can go deeper, but as long as the number of learnable parameters is growing with the scale, the size of the power grid, then it should be good. We use the Atom as the optimizer for the training, 1,000 epochs, and the mini batch size is 32. Okay, now we compared our method, right? The last one, the last bullet, this is our proposed training loss. If you compare with the DC3 and with the NGT, we can see that the key difference lies in the regularize, right? Because the first part, this function f is the generation cost. They are always the same, right? You want to minimize total generation cost, but the only difference lies on the red part. So different schemes, different papers, they have different ideas how to come up with this regularizer. So for the NGT, for the no ground truth methodology, what they have is that they have this penalization on the variable nu. Here, the variable nu is the constraint violation. They also have this x minus x hat. This is essentially what? This is essentially the deviation from your input data. Right? So essentially, they do some convex combination between the constraint violation captured by nu, and also the other term is the load mismatch, because they don't want to see that the recovered load demand deviates from the input too much. Okay, so this is captured by the convex combination of these two, and you have another coefficient here, eta, which is trading off the generation cost with the constraint violation. So that is the NGT. They have the different variable splitting scheme as I talked about. They first output all the voltage phasors as the output of the neural networks, and then they are going to plug it into the powerful solvers, but they are going to plug in the powerful equations in order to figure out all the variables. Second one, for the DC3, we have the same. Actually, we inherit the same variable splitting from the DC3 paper, but the training loss is different. It's different. They only have the training regularizer capture the constraint violation. If you compare with us, we introduced the information from the dual space, right, in order to improve performance here. So we compared these three methods based on these 5 different performance metrics. We have the optimality in terms of the generation cost. We have the feasibility rate, how many constraints are satisfied compared with the total number of constraints. The violation degree, to which extent your vector value function h is positive, and the load mismatch is basically the violation of the nodal balancing equation, and finally the computation time. So let's first see the performance of the NGT. There are lots of details here, but let me try to give you some highlights. If you look at the last column for both two tables, right, the top one is for the IEEE 30 bus system, small power system. The bottom one is for the large system, relatively large or medium size. So no matter for which case, if you look at the load mismatch percentage, so for the small system, it's around 5%. For the large system, it's go beyond 10%, 20%, and the worst case, even like 140% load mismatch. It means that the solution from the NGT probably is not that useful for the operation. You cannot really use it in the real life, okay? Because typically we can say that if the load mismatch is within 1%, it is acceptable for the system operator. But if you go beyond 1%, like 5% or even more than 10% or 100%, it means that your solution is not really feasible. This is for the NGT, and we compared with our method with the DC3, right? So you can see that the first few rows, these are the results for the DC3. There's a weighting parameter lambda for the DC3. You will call the training loss. Right? This lambda is trading off between the generation cost with the constraint violation, right? So it turns out that for the DC3, if you try different values of this lambda, typically you can hopefully try to find a good value for lambda by cross validation, right? But if you try different values, you can see that the generation cost can also be different, slightly different, and also here the average constraint violation mu here and the maximum constraint violation in this third column, they also basically changing over the different values of lambda. Okay, so we compared with DC3. The last two rows are our own method. Either we go with the Newton-Raphson for the power flow solver, or we go with the fast decoupled power flow solver, right? So it turns out that actually we can, if you compare it with DC3, we're like 3 times faster. If you compare our running time with the conventional internal point method, right? We have this mat power. It has the by default internal point solver, we call the MIPS. If you compare running time with it, we get more than 68 times or even 220 times speed ups. Okay, so this is the performance gain from our proposed method. This is about the first work. Any questions before I go to the second work? Yes.
In the algorithm, did you need to compute the mu in the middle? I remember you asked.
Yes, that's a very good question. So if you look at sort of pseudocode of our algorithm, in the second step here, so you take the sample from the data set. You first plug into the fully connected neural network. You get the first variable y. With y, you plug into power flow solver. You get the z1 variable, and mu you start with. Let's say you start with a random guess, initial guess, right? And then you are using this dual ascent, right? So this is subgradient ascent method to update the mu, right? If you want, you can update every iteration, but in this case, we don't have to update every iteration. We can update every 5 or every 10 iterations. Turns out that this can really stabilize the training process and also get better performance.
Another question, in random function, you are also penalizing one side of the inequality constraint. Yeah, but we have power balance as an equality constraint. How does that consider in the penalization?
Okay, that's good. That's very good key observation. So you see that this is the original formulation, right? So all the first four equations, they are equality constraints, as you said, right? All the remains here on the bottom, they are inequality constraints. So inequality constraints will be captured by this H function, but all the equality constraints, they are not captured here. How do we handle them? They're actually handled by this power flow solver. And also, after you get the Z1 and Y, you can figure out what is Z2. Simply just evaluate these 4 equations.
Layers, because you mentioned deep learning, I think single layer is just a simple network. It's not really deep.
Yes, this is like really shallow network. We only have one hidden layer, but it's kind of wide, right? Because we have 50 neurons or 100 neurons. My student, the first author of this work, she tried the deep network. Right? So if you go deeper, you don't have to be wide, but as long as the total number of learnable parameters more or less the same, then architecture probably is not that important.
So we can either try one layer with polynomial, one layer with specified neural.
Yes. Yeah, as long as the total number of learnable parameters are more or less the same, right? And that number of learnable parameters should be increasing with the size of the grid, right? So for example, with the small size HV30, you have 50 neurons, right? When you go with large power grid, you need to have more neurons, right? Or maybe you need to go deeper. I think based on our experience, it's relatively easier to go with the shallow wide network compared to the deeper one. Okay. If you consider about that propagation. But all these kind of things depending on the hardware, depending on how powerful your laptop or workstation is, right? Okay, very good. Yes.
So I'm wondering how you update the parameters of that fully connected neural networks. Is it like purely trained based on input X and output Y, or is it like based on that training error event?
Or for update W?
W is the parameters of that.
Of the neural network. So W is all the weights of the FCAN, fully connected neural network.
I see that. So then how do you update the parameters of W?
So you need to go through back propagation. Actually, I'm going to talk about in our second work. You will see the details. You need to use lots of chain rules in order to update the W.
Yeah, because right, in the calculation of your error, not only those neural network layers, but also that I see the power flow solver.
Correct. Yeah. This is not only this part, because the entire training loss depending on everything here, right? Yeah. So when you do the back propagation, you need to consider about this part. So it's not that straightforward. If you only have this part, for example, I mean, early works, they just fit the X and go into a fully connected network, they output everything. Then you can use the really conventional back propagation, try to update the weights. But this one is, I didn't talk about details because I want to show it in the second work. Okay, yeah, I think I'm really running behind the schedule. So, but if you have already got the big picture of the first work, the second work is relative. We can go more quickly. So the second work is on the semi-supervised learning. Okay, so we have some ground truth labels for those YO. Based on that, actually we train a ridge regression model trying to generate more pseudo labels. Okay, so this is the idea. But more importantly, we're talking about this physics-informed gradient estimation or Jacobian estimation. So the motivation is that we want to reduce the data preparation time, right? So typically you need to use the conventional solver to generate the ground truth label. But in this case, it turns out that even a simple ridge regression model can generate reasonably good quality of the data. So we go with that in order to do the data augmentation. And we accelerate the back propagation step using the batch mean gradient estimation based on the simplified Jacobian. So this is the training loss of the semi-supervised learning framework. Again, we have three terms in our training loss. So as you have already seen in our first work, training loss is really one of the things you need to pay attention to when you are doing research for this topic, because different training loss will essentially affect the final performance, right? There are lots of freedom you can play with when you're trying to design training loss. So in the second work, our training loss consists of three parts. The LO, this is directly the objective function, like the total judgment cost, right? So the LS, this is the penalty for the supervised learning part, right? So in this case, we know what is ground truth data for the active power generation, we call the P tilde. We know what is ground truth voltage phases, we call the V tilde, right? This is our existing labels, or maybe the pseudo labels that we generate, right? So we want to push our predicted value to be closer to the ground truth, right? So this is simply by these two, the sum of two L2 norm of the difference. So this is the supervised learning loss, LS. Finally, we have this LC. This LC is similar like before, is trying to capture the constraint violation, right? So you can have the box constraint violation if they go beyond the C min and the C max, right? You try to essentially project back into the interval. You can simply use the ReLU to evaluate how much constraint violation you have for the box constraint. Now, if you put the three things together, you need to have two weighting parameters in order to have a good trade-off between these three targets. Now, this is essentially come back to his question, how do we do the back propagation, right? Because you have some other modulars in the learning framework, not only the neural network, how to calculate the derivative of the loss function with respect to the neural network weights, right? So we can see that the back propagation essentially try to calculate the derivative of the loss with respect to the training, with respect to the weighting parameter W of the neural network, right? So this can be simply factorized as dl over dy. So dl, again, this is derivative of the loss with respect to the output of the neural network. And the second factor is dy over dw. So dy over dw is very straightforward, right? Because y is output of neural network, w is the weight. So depending on the neural network structure, we know how to simply calculate dy over dw. The only difficult one for our framework here, for both the second work and the previous work, is trying to calculate this red factor, dl over dy, right? So for this, we are using the chain rule. There are lots of detailed mathematics here. We don't have time to go through details. But it turns out that if you want to find out the first factor, you need to find some other derivatives or partial derivatives. For example, this blue one, dz2 over dy, right? Remember that z2 and y, both of they are part of the output variables. And also need to calculate what is dzy over dy, right? So the next slide showing that to calculate this derivative dzy over dy, simply we can use the implicit function theorem, because the z1 and y, they are essentially correlated via this power flow solver, right? They are essentially correlated by the AC power flow equations. So using this implicit function theorem, we should be able to calculate the dz1 over dy. Okay. Again, there are lots of other details here, but generally speaking, many other factors here. In equation 6 and 7, we can extract information from the nodal Jacobian matrix and the branch Jacobian matrix. Okay, so this is sort of high-level things. And at the end of the day, there will be some matrix inversion here, but we know that we don't have to go with the matrix inversion because usually it's very computationally heavy. We can simply try to solve the related linear system, because even though computational-wise, the complexity is the cubic, the same is the cubic computational complexity, but solving a linear system is more numerically stable compared with the directly inverting the matrix. Okay, so if you go with the 12 and 13, we should be able to finally calculate this factor partial L over dl over dy. And the next things we want to briefly discuss is about how to find all those Jacobian matrices, right? So because all those partial derivatives relies on the nodal and branch Jacobian matrices, and if we can efficiently evaluate or estimate those gradients, then it can really accelerate the training process. Okay, so imagine that we are doing a mini batch training, right? So basically, we have a large data set, we truncate it into different groups, different mini batch. Each mini batch has certain samples, right? Typically, it's like 32 samples, 64 samples, so on and so forth. And we can see that those Jacobian matrices in the mini batch training setup will become or generalize to be a tensor, right? It's no longer a two-dimensional matrix. It becomes a three-dimensional matrix, like a tensor, right? So the last dimension, this B, is precisely the mini batch size. Now, if you go with this mini batch training, then it turns out that if even you go with the solving the linear system, the complexity is cubic in the power grid size, right? Here, the ND is number of PQ bus, NG is number of PV bus, right? But on top of that, you have to have this mini batch size involved in the computational complexity, and you need to do this every iteration, right? This is too much. We cannot really afford it. Especially if you want to talk about real-time applications, even for the training, right? So with this, actually we propose 3 different ways to elevate or reduce the computational burden. So we have the linearized Jacobian, we have the decoupled Jacobian, and finally we have the batch mean Jacobian, right? So the linear Jacobian is straightforward. It's pretty much like AC-OPF's power flow models, whereas we have the condition saying that if all the angle difference is small, we can approximate the theta, we can approximate the sin theta with theta, cosine theta is roughly 1. And we assume that all the magnitude are close to 1 per unit. In this case, we can replace some of the voltage magnitude Vi or Vj with 1. After we do all this linearization, it turns out that in order to calculate the Jacobian, here is the sum of the elements of the Jacobian, you're simply sort of just evaluating a linear system. The decoupled Jacobian, this is from the decoupled power flow solver idea, because we know that there's a weak coupling between the P and V, Q and C. In this case, if you look at the 4 different blocks, in the Jacobian matrix, we see that those two blue blocks in the off-diagonal direction, we can approximate using the 0 matrices, right? So with this, we keep the two main blocks the same as before. We can essentially reduce the computation complexity a little bit. Essentially, we don't need to solve a large scale linear system. We can essentially bring it into two separate small linear systems to deal with. And finally, this is the batch mean Jacobian estimation. So remember that we have the third dimension to capture the mini batch, right? So without going into too much details here, the high level idea is trying to take the average over the third dimension. Essentially, you compress the data over the mini batch dimension, right? I consider that, okay, what's the average value along the third dimension? And that is, we are going to use the corresponding counterpart from the tensor. We call the T bar and the Tij bar. This is taking the average over the mini batch dimension. And also we have the sort of the good reason to do that, because it turns out that this approximation error is that using all the samples, but using the average value of it, the error is really small. Okay, so we see that supervised learning, heavy computational burden, unsupervised learning, there's no Y, we don't know the ground truth labels, and something in between is the semi-supervised learning. We can essentially train our ridge regression to predict all those Y hat. Okay, so this is about data generation, and then we simulate for these benchmark systems. We have the IEEE 118. We have the PGAT system. This is a European transmission networks. The largest one probably is more than 9,000 buses. So we have 4,000 samples for the PGAS 9241, and for all the remaining three systems, we have the 10,000 samples. So similar as before, we can generate data for PD and QD. In this case, we have the 20% deviation around the normal values. And for the second work, we don't even have the server. We just try with the iMac, even without the GPU, I guess. So again, similarly, we compare the different methods with those 5 performance metrics. Here, the new thing is that we have the storage. We want to show that how much storage we can save, memory size we can save by using batch mean Jacobian estimation. Now, let me show you some result here. I just focused on the 2 large systems that we simulated, right? So here, the M4 is our proposed method with the linearized decoupled Jacobian, and also we consider the batch mean. So if you look at the storage, right, of course, semi-supervised learning in terms of the memory size cannot beat with the 0th order, right? The 0th order is just simply rely on the function value. You don't even need to have the first order information. But if you compare it with the full Jacobian, right, we save a lot of storage here. And also in terms of running time or training time, small t, this is the per epoch training time, while the big T, this is the total training time. So we can see that our simulation time, training time, is much better compared with the full Jacobian case if you talk about the DC3 paper or some other early works. So if you compare it with the max power interior point method, the speed up is huge, right? For the 2869 bus system, if you use the interior point method, the solving time is more than almost 110 minutes. But if you go with our proposed method, of course, we are talking about the test phase, right? Testing phase is only 50 seconds. So essentially, all the idea about using deep learning to replace the conventional solver is what? Is to shift the computational burden to the training time. And when it comes to testing, everything is simple, right? It's straightforward. It's much faster than the conventional solver, right? But for the training time, we can afford it typically, right? Usually do the training offline, right? And after we train a good model, we can use in the future. Right? It's like the large language models, ChatGPT. After you get a good model, you can give it a new prompt. You can get a new result. The same here, right? So all the computation burden will be shifted to the training phase, and you make your testing phase life much easier. Okay, so there are some results here. We show that our proposed method, in terms of the training loss trajectory, is really close to the ground truth Jacobian. Remember that I talked about the estimation error is really small. But if you go with the zeroth order estimation without the correct information of the first order derivatives, you can see that there's a huge difference, right? So the takeaway message is that whenever you can use first order information, try to use it, but you can do some kind of approximation, try to reduce the computation time. Okay, let me skip some other results here, and I want to quickly get through the last topic, right? A few minutes. Okay, maybe I think, yeah, maybe let me please skip the third work, because third work, I mean, this is still under review, but if you feel interested, I'm more than happy to discuss with you offline. So the big idea is trying to, again, use the deep neural networks, trying to identify which constraints are active or binding. For those non-binding constraints, you can remove them before you plug in problem into the solver, and this can reduce the constraint size and can essentially reduce the solving time. Okay, so this last one. So let me directly jump to the summary. So the summary, the takeaway points I want to really capture here. For the first two works, we see that by using the Lagrange duality, right? So the OPF solution can be learned even without the true labels. This is for the unsupervised learning. If you have a good training losses to design. The variable splitting is really important because different variable splitting techniques may result in different degree, constraint violation degree, and load mismatch. And then finally, the efficient Jacobian estimation is crucial for the fast training. And for the third work, we didn't have time to cover. Essentially, we say that try to use the mixture of experts framework, bring different experts, different architecture of your neural network, and leverage the advantage of each of the network in order to improve the performance. So some future directions, right? So if we consider about directly apply our proposed framework, of course, we can try to think about all those OPF variants, which I talked about at the very beginning, right? These days, you can even think about trying to combine reinforcement learning with deep learning framework in order to deal with the dynamic OPF. And you can also consider about solve OPF together with the unit commitment, right? This is going to be much harder because you have the binary constraint, you have the binary variables, and how can we come up with a scalable and reliable learning models, even try to deal with uncertain topology variations, because this is a real problem these days. Many utility companies, they don't even know what is the topology of the network, because some of the lines may be already switched off, or maybe they already changed the topology, they don't have a good records in their system. So they don't have the 100% information of the distribution topology. And finally, right, we're talking about foundation models, large language models for the OPF, or maybe even for some other great operations. Right? I know that many groups have already started efforts in this direction. But again, the common challenge in this emerging efforts is that how can we get good enough or high quality and diverse data? Right? Because typically for the history data or real data, they may not large enough, or they may not really diversified enough. So if we want to use some data augmentation technique, then how can we come up with a diverse data? Of course, we need to satisfy all the physics, right? All the laws of physics for the feasibility. And most importantly, as everybody knows in this community, no matter what fancy architecture or fancy algorithm you are going to come up with, do you have a good interpretation of the results? Right? If you don't have good interpretation, it's more like a black box, right? So we said, okay, try this, it turns out to be good, use it. It's okay, but if we can provide a really theoretical explanations, foundations to justify why this is good or why this is not good, then it's more desirable, right? So this good interpretability about deep learning is really the efforts that we are putting efforts on. Okay, with this, I just finished my talk. I'm going to skip some other topics here. And thank you very much. This is the funding support of these works. And this is my group. And all the credits to my students for the talk that I covered today, especially the first two students here, Kejun Chen and Xiaoyue Both. So Kejun is the leading author for the first two works. Xiaoyue Both is the last one that we didn't get time to cover into details. Dr. Jin Xiong and Gabriel Intriago, they graduated last year. They joined some AI companies in the Bay Area, or maybe in Seattle. CFAT, she's working on the system grid hardening, right? Trying to deal with the multi-hazards to decide which power lines we need to on the ground or keep overhead. And Kunjin is an excellent student. He contributed a lot into the fault detection mechanism. So with this, I finish my talk. Thank you very much for your attention, and I'm happy to take any questions you may have.